All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be looking at is the basic atomic structure of atoms, and we'll also look at some of the differences between the atomic mass unit and atomic weight. So we're going to cover quite a number of sections here. And so before we get going, there's several objectives I would like you to be able to meet by the end of these notes. So objective number 1 is to describe the composition of an atom in terms of protons, neutrons, and electrons. Objective 2, give the approximate size, relative mass, and charge of an atom, proton, neutron, and electron. Objective 3, write the chemical symbol for an isotope of an element having been given its mass number and its atomic number, and perform the reverse operation. Objective 4, describe the properties of the electron as seen in cathode rays. You also need to describe the means by which J.J. Thomson determined the ratio for that electron to mass ratio. Objective 5, describe Milliken's oil drop experiment and indicate which property of the electron he was able to measure. Objective 6, cite the evidence from studies of radioactivity for the existence of subatomic particles. Objective 7, describe the experimental evidence for the nuclear nature of the atom. Objective 8, use the unit of atomic mass unit in calculation of masses of atoms. And objective 9, determine the term atomic weight and calculate the atomic weight of an element given its natural distribution of isotopes and isotopic measurements. All right, so we have quite a number of objectives. Hopefully this should be a little bit of review, but just as a reminder here, the highlighted words that I have in yellow are the ones that you need to copy down, as well as the information that I will add as I go through these particular notes. So we start out here with what is the atom in the 3 basic subatomic particles. Now, we can get a little bit more in depth and in detail, and there's actually been quite a bit of research on the further or the more smaller or the smaller types of particles. But we're going to stick with protons, neutrons, and electrons for this class, as are 3 basic subatomic particles that make up the atoms. So you can see here that by 1850, which a little over 150 years ago, scientists knew that each atom had these 3 particles: protons, neutrons, and electrons. And what we have here, this is a pretty good depiction of our current model of the atom. I know it may be hard to see in the video, but what we have here is this negative electrons, and they show it in this pink cloud here. And this was an early model of the atom, and we'll call this the Plum Pudding model and get to it here in a second. But a really good review of where our pieces or particles are in our atom is this. Our positive proton and our N4 neutron is in that center, in that nucleus, and then around the outside. It's not fully correct to have this in here. Around the outside is that electron. Okay, so the positive here is the proton. The N is our neutron, which is neutrally charged, and we'll get to that in a second. And then that minus symbol there is for our electron. So let's keep in mind that that is our basic structure. And what we're going to do here in the next couple of pages of notes is we are going to see how scientists were able to determine those 3 basic subatomic particles. Now I have down here at the bottom that electrostatic attraction says that likes repel and opposites attract. So that means protons are going to repel other protons, electrons are going to repel other electrons, and protons and electrons are going to attract each other. And really, I like to think about this in terms of magnets. So I'm going to put think like magnets. Opposites attract, likes repel. Okay? So we have to keep this basic knowledge in mind as we go through the process of determining how they found the atom. All right, so let's move on here before we spend any more time on this page of notes, and let's transition to our next page here. All right, so what we have here, I've already mentioned this, so I will just do this in passing, but this is our definitions here of our three subatomic particles. One, we have the proton, which is the positively charged particle in the nucleus. Remember, the nucleus, just as a reminder here, is the center of the atom. That is the basics or the setup of where we have our protons and neutrons. Now, the neutron is the neutrally charged particle. It's also in the nucleus. And then we have the electron, which is negatively charged and located outside of the nucleus. Now, notice here that the electron, it states that it takes up most of the volume of the atom. Most of the mass is going to be from protons and neutrons, which we'll talk about here down below, and most of the volume is going to be from that electron. The other thing I want you to turn your attention to is this particular picture. Now, this is a generalized picture, but it shows a little blue dot right here in that center, and that is the nucleus, and it contains both the protons and the neutrons. So think about this for a second. Most of the mass is in this little tiny dot in the center, called the nucleus, and most of the volume is these electrons, which the picture shows here as a red cloud. So the nucleus itself is going to be a very, very dense region that contains most of the mass. The other thing that I want you to notice here is the relative size of an atom. Now, the relative size of an atom, we see here, this is 1.5 angstroms, and angstroms is a special unit we use in chemistry to be able to describe the size. Because atoms are very, very small, an angstrom is also very small. It's, I think, 1 times 10 to the negative 10th meters. I'll have to double check that, but that is how minutely small an atom is. And then notice here in the nucleus of this generic atom is 1 times 10 to the negative 4th angstroms. Okay, so again, angstroms is about 1 times 10 to the negative 10th meters, and so that's a very, very small particle. All right, so I've already mentioned this, but the nucleus is the dense region, contains the protons and neutrons, and that itself, the protons and neutrons, make up most of the mass. Now, yes, the electrons, because they are matter, they do occupy space and they do have to have mass, but relative to those protons and neutrons, it's not as big. All right, so again, let's keep going over some really administrative data is what I'd like to call this. But we get to our charges of our subatomic particles. Now, this I'm not as concerned about, but it is important to know what the charges are. So every proton and electron is going to have the same quantity as this value we see here. Now it's 1.602 times 10 to the negative 19th coulombs. Now that may sound familiar, especially if you have a physics background, because that number is sometimes utilized in some electricity calculations. You could also, if you're dealing with physics, not so much on the chemistry side, but you could convert this to a joule per second, and sometimes that has some other applications that can be utilized. But I want you to notice this, that the charge of an electron is negative, that value we just discussed, and the charge of a proton is positive. Now, in chemistry, especially in this class where we're just introducing the basic concepts of most things chemistry, those numbers can get confusing, and we can use this exponent business here. What we need to worry about here is we're going to have this relative charge, or as the notes express it here, the multiples of these particular charges. Now, electrons are going to have a 1 minus charge and a 1 plus charge. Again, this all stems from, this is the exact value or the exact charge, but we're going to say, hey, our electron charge balances out our proton charge. Now, with this, we have atoms with equal number of protons and electrons have no electrical charge. Let's simplify this here and just say that atoms that abide by this point down here are known as neutral atoms. And until we get talking about ions, or until we get talking about charged particles, we're going to consider atoms to be neutral unless stated, or like I said, we're working with those particular ions. Okay, so again, I'm not too concerned about this. The biggest thing here is our plus and excuse me, our plus and minus charge. Okay, so now we have the basic information out of the way, we can start talking about a little bit of the history of how did we get to this point of having these three subatomic particles. Okay, so we're going to go through a little bit of a history lesson, but it's important really from a scientific standpoint to realize and understand, well, what experiments did scientists have to do, and how are they doing those experiments, or what equipment they were using. So early on, they had this idea, and you can see way back in 370 BC, they had a lot of Greek philosophers, and a lot of them were actually pretty close in predicting what happened with our matter. And they said, hey, they had these indivisible parts, meaning they couldn't be divided any further and retain their properties. And unfortunately, they didn't have the scientific equipment to really test that. All right. So again, this came from really early on philosophers. They just couldn't support that with their data. So along comes the 1800s here, and we get a gentleman, a scientist by the name of John Dalton. And Dalton did some research and made a theory. Now, this theory right here, you need to know all 4 points of his theory. So I will say need to know all 4 points, okay? And so what John Dalton did, again, he had some evidence by this point, but he said that elements that we find on the periodic table of elements are composed of atoms. Now, atoms of an individual element, so one single element, are identical. We'll get to how they are identical here in a second, but they were identical. And then he also said, and this is really from his experimental data, was that in a chemical reaction, the atoms are not broken down, They are just changed and rearranged. They are just changed and rearranged into different types of atoms. Now, the compounds are going to form when those atoms rearrange and recombine or break apart with one another. And so basically what we had here was that the basic premise for how we were able to base our work around the atom. So you may be wondering, okay, well, where did Dalton get this information? Well, like I said, he did a lot of experiments, and that helps explain point C here. And those experiments actually led to a few laws. So to help support Dalton's atomic theory, we have his laws, okay? And so the law of constant consumption, conservation of mass, and multiple proportions. You can read in depth and in detail about that, but what these laws basically explained is, hey, when we have a chemical reaction, we are going to get some equal parts. We are going to get some equal parts into what we have here. All right, so again, it's important to note that Dalton had this type of information, these laws to help support them, and what he said about atoms also countered that and helped support this. Again, I'm not too worried about getting into the details of these. It's just good to have an idea about where Dalton got that support from. All right, so now let's get down to business here. How did we discover that the atom had protons, neutrons, and electrons? So we start actually with finding out about the electron. So again, we're in the mid-1800s, and remember from the beginning of the notes, the mid-1850s, around 1850, scientists had determined they had protons, neutrons, and electrons. So a relatively quick set of work from John Dalton's theory or his atomic theory. So we start here, and we're in the mid-1800s, and we have these cathode rays. And so a cathode ray, it says here, is radiation produced when high voltage is applied across a tube. Well, let's break this into layman's term. Electricity flows through vacuum tube. Okay, so yeah, let's keep that relatively simple. Now, electricity, we already know here, is typically talking about the movement of electrons. So I'm going to have a definition within a definition here. And so basically we're talking about electrons moving through a vacuum tube. Well, okay. This vacuum tube here we can see is moving from the negative to the positive electrode. Now from electrochemistry, we know that negative electrode to be the cathode and the positive to be the anode. So if you have an in-depth knowledge on electrochemistry, that's the natural flow of electrons, okay? And so this is really important. The electrons can be altered by the presence of a magnetic field. So remember, scientists are shooting electricity through this vacuum sealed tube, which means there's no other matter, but it can get affected by a magnet. Now remember, a magnet has a plus and minus charge, and so if we put a plus or a minus charge, we can determine the charge of that electron. So what happened what happened is this. I mean, the scientists in the mid-1850s had these cathode rays. They also were very particular about putting plus and minus charged magnets, and they were able to use those plus and minus charges to determine what the charge of that electron would be. Now, they went one step further. They could fine-tune these magnets to deflect the charge of the particular electrons, and by determining or having a particular strength of a magnet, they could determine this charge to mass ratio. Ultimately, that means, hey, well, we are going to be able to find out the actual mass of the electron. Okay? So, what happens here is this. This is the first time that we actually identify some subatomic particles, some pieces and parts that make up those atoms, which are the building blocks of matter and are the basis for each individual element. We're able to pinpoint one particular point or one particular part that makes up those atoms. All right. So yes, we had a cathode ray tube. It had that deflection of charges, and that helps us determine what the charge is, number one, and also it helps us determine what the mass of an electron is. Now, what happens here specifically is this. J.J. Thomson, he is the one to do this charge to mass ratio. Now, he does it and he finds the charge to mass ratio, but he develops this plum pudding model. Now, I'm going to have a very crude model, but his plum pudding model was this. Imagine this entire area that I have circled here is just a overall positive sphere. And then embedded in that sphere is those electrons. So the electrons were, quote unquote, the plums in the plum pudding. The pudding itself was that overall positive charge that those electrons were nestled in. Again, very crude model, but that is one of our first models that we have here. All right, we will keep moving on here to Robert Milliken's experiment. So Robert Milliken, again, what he wanted to do specifically is find out the actual mass of an electron. And I know I kind of jumped ahead of myself, but what he did was this oil drop experiment. And basically he knew about the charges, he knew about the specific charge of that electron, and you can see that charge to mass ratio that J.J. Thomson was able to develop. He utilized that in his calculation. Again, basically what happened is he utilized the positive and negative charges through his apparatus, and he was able to determine the mass of an electron. Again, use special calculations to be able to get to that point, but the important thing here is, hey, Milliken utilized Thomson's information along with his own experiment to be able to find out what the charge of an electron is. Now, here is the really important point. We get to this point and we still have J.J. Thomson's plum pudding model. Again, one of our first models of the atom. But this next experiment here, and I'll change the page here, this next experiment is crucial. And this is Ernest Rutherford's gold foil experiment, and he's able to determine or have the nuclear model of the atom. So what he does, he shoots these alpha particles, which we'll learn in a little bit here what an alpha particle is, but we just need to know for right now, alpha is a positively charged particle. And so what Rutherford does is he shoots these alpha particles into a very, very thin piece of gold foil. And what he was expecting was different than what he got. So you see here, most of the alpha particles went straight through. Very, very few alpha particles were repelled. And so what this means here is that we need an alteration of what Rutherford or what Thomson's model was to explain Rutherford's experiments. And let me correlate these two things here. Okay, so if J.J. Thomson's model was correct, and we had this overall sphere of positive charge, most of them should have been repelled. However, most went straight through. They weren't repelled or deflected. So, important thing about Ernest Rutherford's model, or Ernest Rutherford's experiment, is it says we need a different model. Okay? So, Rutherford's results. 1, he took and he used Thomson's explanation here, and he said, hey, yeah, the atom's most likely spherical shaped, and because most of my positive alpha particles went straight through, that means we have to have a positive center. The negative part is going to surround it. So now we have this first idea of the nucleus, which I'll draw down here. Again, I'm going to draw it as a plus for a positive. And it's a later experiment. We don't actually talk about it. Is by the scientist named Chadwick. He discovers the neutron. Again, I'm not going to talk about that. But they say, hey, there has to be a positive center or a positive nucleus. Around the outside is this electron. So again, we started notes out with this particular model, and we end with this particular model here. We go a little bit further with Rutherford's model, and we are able to develop a more concise idea about electrons. But for right now, this is a really good model, and it helps explain each of the locations of the 3 subatomic particles that we're concerned about in this class. And that is your proton, neutron, and your electron. Okay, so again, kind of a brief history lesson. Now we can kind of jump back into the business of chemistry, okay? So with chemistry here, we have the basis of protons, neutrons, and electrons. We know that each element is composed of a specific type of atom. The one thing that was unique or that didn't hold true for Dalton's atomic theory was this. I'm going to write it down on the next page. But he said all atoms of a single element are identical. And again, I'm gonna write this down because this is significant here. We discover isotopes. This isotope here, it says defined as an atom with identical atomic numbers but different mass numbers. Okay? So that means atomic numbers, again, is talking about your number of protons. Number of protons. We can have something with the same number of protons but different number of neutrons. That's what that means to have a different mass. So again, by finding out that we have isotopes of each and every element, this disproves one part of Dalton's theory. So let me pause, write it down so I'm coherent when I write this particular statement down. All right, so there we go. Again, Dalton said in his atomic theory, all atoms of one element are identical. Again, because they found isotopes, they did further and further work on atoms. Because they found that part of his theory can't be true. Pretty good theory, just this one little flaw here. All right, so that means that we are going to have elements, or we are going to have atoms with the same number of protons, but their neutrons vary, okay? And so we need to represent what particular isotope we have, and the way in which we do that is through our isotope notation. So we get to our isotope notation, and I have some generic symbols here. And so I have a capital X that represents the element symbol. The superscript A represents the mass number, and the Z represents the number of protons. Now, remember, number of protons is equal to what we call our atomic number. Same thing as number of protons, that big whole number that we have on the periodic table. Our example here is carbon-14. Now, we represent that with a 14 in the upper left-hand corner of the C, the element. That means that's the atomic mass. And then down below is the number of protons, which is that whole number that we find in carbon. All right, so the other way, we don't have to represent it through our I call this the symbol notation. We can also write it out in this form, okay? We can have our element name followed by the mass number. So again, carbon-12, just like we had, this is a new example. Carbon-12 would be representing, that 12 represents the mass number. Now, the other thing that I want to point out, and I'm not going to waste time here, but the mass number is equal to the number of protons plus the number of neutrons. So we need that to be able to correctly identify some calculations involving this isotope notation. So let me go ahead, let's flip the page, and let's go on